Okay, on 4.6. Tangent is an odd function. Therefore, if you put in a negative of it, you get the negative function. So when we look at tangent sine over cosine, it's going to be undefined at cosine is the value of 0. So when we look at our cosine picture looks like this. All right, where this is 0, this is 2 pi, this is pi. That means that's pi over 2, and that's 3 pi over 2. What this says is that in the tangent picture, pi over 2 and every pi over 2 value is going to be undefined. So if I went negatively, I would be over here at negative pi over 2. So that gives us our boundaries for tangent. Now remember when we just did sine and cosine the last few days, sine and cosine had boundaries at 0 and 2 pi. Well, tangent is going to have boundaries at negative pi over 2 and pi over 2. You need to be able to fill in a t-table according to that. If you have x and tangent of it, those are the values that you get. So what's going to be happening here is that it's going to increase, meaning from left to right it's going to go up. And it means it's approaching the asymptotes. Halfway between, it's going to hit the 0. So our tangent lines, at every pi over 2, there's going to be a asymptote, and our tangent line is going to cross halfway between. So that's what a tangent is going to look like. Whether it's positively or negatively, every pi over 2 is going to contain a wave that is increasing. So every n pi of pi over 2, because at 90 degrees, then the next one's at 100 and 270, add another 180, subtract 180, subtract. So it's at 180 degrees off of 90, if you want to look at it instead of pi and pi over 2. Okay. Second page. So the period of tangent is going to be a pi. The domain is restricted to strictly the pi over 2. And then every 180 degrees after that. The range is negative infinity, positive infinity, and the vertical asymptotes are at pi over 2 and every pi over 2. So notice the asymptotes are at the exceptions. That will always be true. We always graph our intercepts and our asymptotes when it comes to finding our tangents. And then our boundaries are set by setting the bx minus c to negative x over pi over 2 and positive pi over 2. And between each of them are going to be the intercepts. So there's my pi over 2, and this is my asymptote. Remember asymptotes from before are dashed lines. You are required to put in dashed lines as your asymptotes. So if we're going to graph, here we have y equals x over 2. So we found our boundaries. Set that bx minus c part, in this case is just a bx, to negative pi over 2 and pi over 2, and you find your boundaries. Negative pi positive pi. Halfway between that is where it's going to cross the x-axis, and it's going to continue approaching those asymptotes. And you are good with the 1 period, right? But I drew out more just so you could see them. Here we have sketching some more points just so that you can come up with a more accurate graph. So here at negative pi over 2, there's my negative 1. 0. At 1, we have positive 1. Pi over 2, we have positive 1. Just gives a more accurate curve and a more accurate graph. And when it comes to these tangent and cotangents, you will be asked to fill in a t-table accordingly. So here, negative 3, well, the negative means it inverts it. So instead of increasing from left to right, it's going to decrease from left to right. The bx we set to the boundaries, negative pi over 2 and positive pi over 2. So the boundaries are negative pi over 4 and pi over 4. That's one cycle. Now make your graph a little bit more accurate by filling in the t-table. So undefined, pi over 8 halfway, which is 3, 0 halfway of the beginning and end, another halfway is negative 3, and then approaching undefined. So again, it's just making it a smoother graph. When it comes to cotangent, with cotangent, the period is with pi, but the boundaries are 0 in pi. That means when we're setting our bx minus c, we set it to 0 and pi. So we have 3 different boundaries. Sine and cosine have one. Tangent has one. And cotangent has a different one. So in this case, we have 2 cotangent of x over 3. We set the part to our first boundary of 0, second boundary of pi, and we fill in some more exact points. Cotangent and tangent are reciprocals of each other, so it makes sense that cotangent would go downwards, whereas tangent increases, cotangent decreases. 0 and pi are going to be the boundaries. In this case, it happens to be 0 and pi as well. And then find some more exact points so that you can have a cleaner graph. All right, cosecant and secant. Cosecant and secant are reciprocals. They are reciprocals of our sine and our cosine. So their graphs are going to somewhat be based on the graph of sine and cosine. They have asymptotes just like tangent and cotangent does. For cosecant and cotangent, the asymptotes are at every pi values, or 0 and every pi value thereafter. Secant and tangent have asymptotes at 90 degrees and every 90 degrees, so every 180 past 90, 90 to 70, and so on. So what's going to happen is that the sine wave and the cosecant, because those are the cousins of each other, here's my sine. Okay, sine is at 0, pi, 2 pi. There's 3 pi over 2, and there's just pi over 2. All right. The cousins are going to have asymptotes where it is a 0. So cosecant has an asymptote wherever there's a 0, and a 0 is an x-intercept. Then the cousins reciprocate, they flip. So what happens is on a sine wave, the maximum point ends up being the minimum point of the cosecant. Therefore, the minimum now becomes the maximum of the cosecant. So the points on the sine is what creates the points of the cosecant. You have to know your sine and cosine in order to find secant and cosecant. So looking at the one that's on the picture here, here's our normal sine wave, asymptotes on the zeros, and whatever those points are, it's going to reciprocate. It's going to flip them up. So this one is going up, it's going to flip it down. So if you drew just a cosecant wave, you would have your asymptotes, and you would just have parabola shapes. Okay, so let's then look at the same thing happens with cosine. Here's a normal cosine. That's a normal cosine. So the cousin secant is going to be at the intercepts, the x-intercepts, and it reverses from the points. So again, if I were just to draw this separately, I would see something like that. The cousins are going to be reciprocals. They're going to be up and down parabola type shapes. And they're always going to have asymptotes at wherever the major has a 0 x-intercept. All right, and then the last page of the notes, f of x equals x sine x is the product of two functions. When you have those two functions, they combine together. So y equals x is a line. So there's y equals x. And then we have its counterpart, y equals negative x. The sine of x is a curve or a wave that happens to be in between it. So what happens is that the linear bounds the wave, and you get this harmonic motion. Another one that's on like page 340, here you have e to the negative x. Well, e is a logarithmic or an exponential here that's going to have a curvature. Sine is going to be this wave, so the wave gets compressed between the exponential function. So that's just a dampened or harmonic kind of shape that you would see. Another one to look at there on page 340. So there's 4.6.